Okay, I guess give a short intro now. So, everyone, welcome to the third talk of the space mission series. This talk will be on Chandrayaan 2 by Arjit Shankar Banerjee of BSMS 2020. Yeah, Arjit is a very familiar face in Celestic, so I'm sure you're all familiar with him. So yeah, can go ahead now.
Yeah. Okay. So, hello everyone. Myself Arjit Shankar Banerjee and I'm from BSMS 2020 batch. So, today I'm going to deliver a talk on pretty much famous topic like Chandrayaan 2. We all must have heard about it at some point of time because it was on in the headlines for like quite a long time. So, it's part of the space mission series. So, let's begin. Yeah. Uh, yeah, I'll start my talk by giving just some general information about this Chandrayaan 2 mission. And after that, I'll try to introduce you to some new topics, some detailed information about this. I'll go through each part one by one, and I'll try to keep the sessions interactive. I'll be asking few questions in the middle, so try to answer that if you know. Otherwise, I'll be answering that. And if you have any kind of doubts, obviously you can ask like maybe by interrupting me or maybe towards the end as you wish. So yeah. So some general information about the Chandrayaan 2 mission is obviously as the name suggests, it's Chandrayaan 2. So it was the second moon mission after Chandrayaan 1. So why Chandrayaan 1 is famous? So Chandrayaan 1 was the moon mission by ISRO that proved that water exists in moon. So its launch date was 18 September 2008. Now, this Chandrayaan 2 mission was launched on 22nd of July 2019, and its total budget, like including the launch vehicle, like the spacecraft, as well as the spacecraft as well as the GSLV Mark 3 rocket, including both, it was around 978 crores approximately. Out of them, 603 crores was for the spacecraft that was exclusively made for this mission, and this GSLV Mark 3 rocket, which was around like 375 crores. Now you can see that this is less than even 1,000 crores, and I would say like if you are only taking into account the spacecraft, which is around 603 crores, it is like much lesser than the other lunar missions that has been done by any other space agencies such as NASA or European Space Agency or like Russian Space Agency or etc. Now it's total what I mean to say is that it is very cost effective mission, and the total mission weight was around like 3,850 kg. I've added a fun fact here that this launch was earlier scheduled for around 15th of July to 2:51 a.m. at night in the morning. So, but it was stopped at like T minus 56 minutes because like they noticed some kind of technical flag while they were loading the cryogenic fuel in that. So later on, it was delayed to like 22nd of July, and on 22nd of July, it was launched successfully. Now, let's talk about like why they carried out this Chandrayaan 2 mission and like what were the main aims of this mission. So the main aim of this mission was to enhance our understanding of Moon by studying not just one area but all the areas including the exosphere, the surface, and as well as the subsurface of Moon in one mission itself. So they were trying to carry out this mission. Like it was a pretty complex mission, I would say, and they tried to look into a broader perspective. They tried to gather a lot of information in one mission itself, and it also aimed to stimulate the advancement of technology, promote global alliances, and inspire future generation of explorers and scientists. Another fun fact with this was like with this mission, India became the first ever country to reach the lunar south pole. Like be it successful or not, like it touched the lunar south pole, and it was the fourth ever country that landed a probe on moon. So first three were like USA, Russia, and China. But that landing part wasn't that much successful, but it landed somehow. It suffered a hard landing, I would say. So yeah, we'll talk about that. Now these are some more aims. So one of them was like that Chandrayaan 2 mission. It had like several science payloads to expand the lunar scientific knowledge. To like what it aimed basically was to study the topography, the seismography, mineral identification distribution, as well as the chemical composition, the temperature around, like what's the atmosphere, what kind of, like, is there any atmosphere on moon, like there were, like, as you can see, like this is a pretty wordy slide where, like, they tried to carry out, like, lot of they tried to gather a lot of information with this one mission itself. Another point was that it is like it had like around three stages. I'll come to that in detail later. So the one of the stage was that the one of the part was that the orbiter, and the other two were the lander and the rover. So this orbiter was had the remote sensing technology, which was supposed to, like, um, carry out the remote sensing observations. And the other two parts, that is the lander and the rover, would have performed the in situ measurements. And what you must be wondering, like, what is in situ? In situ means, like, on the lunar surface itself, while the orbiter would be, like, revolving around the moon. And yeah, one more thing, like orbiter is, like, still functional. Now, for understanding lunar composition, it was planned to identify the elements and mapping its distribution on the lunar surface, both at global as well as the in situ level. Now, another thing that they tried to do was, like, water molecular distribution. That would have been done using the infrared spectroscopy, the synthetic aperture radiometry and polarimetry, as well as the mass spectroscopy techniques. I'm not going into too much details into that. As we will proceed, I'll introduce to you, like, one by one, what all machines or what all type of equipments they sent to the moon and what all were the functions of them. And I'll try to keep it like, I'll start from the basic level and try to advance bit by bit so that you all can understand. Now, one obvious question would be arising in your mind, would be like, why lunar south pole? Like, why exactly they chose this lunar south pole itself? Why not any other part of the moon? Was it just like something fancy that no one touched it, so we would try to do that? The answer is no. The main point about it is that it was a, like, special interest to scientists because they predicted that water ice might be present in the shadowed areas in the lunar south pole. The lunar south pole region features, like, around craters that are unique in the near constant sunlight. Like, it means that the lunar south pole, uh, much of the sunlight does not reach that portion. So they all thought, like, there might be some like more amount of water might be present in that in those particular areas. So from the Chandrayaan 1 mission, we already proved that water exists on the moon. And with this Chandrayaan 2 mission, they tried to increase their what to say, like, they tried to understand, like, whether they it in what all areas it's present. Now, one more thing I want to add here is that the lunar North Pole region is much shorter, like smaller than the lunar South Pole region. So, and whole of the lunar South Pole region was, like, unexplored. So they all were thinking, like, they would be exploring the lunar South Pole region. Another very important point is this, the third point, that the South Pole regions has some craters that had coal traps and contains fossil record of the early solar system. So the thing here is that, like, these particular, such craters are coal traps, like, that contains fossil record of hydrogen, water ice, and other volatiles dating from the early solar system. So they also aimed that they might get some information about how our solar system evolved. Um, those questions might have been answered if, like, it would have been, like, if the lander and the rover would have been successful. I'll come to that. So they also aim to study about the early solar system using this, by exploring the lunar south pole. Now, this was some prerequisites, I would say, like the some general information and the aim. Now, before uh, going forward to my talk, I would like to introduce some, like, terms which I would be using throughout the talk. So I'll be introducing it earlier only, and obviously, like, there are more terms that I would be using, but in case these are the most prominent ones, and if I am saying anything else other than these, then I will be explaining it there only. Otherwise, you can obviously ask me towards the end. So the first one is, like, the probe. So probe is nothing but a spacecraft that travels to the space to collect scientific information. Then cryogenic fuel. Now, what is cryogenic fuel? This word you might have heard a lot of time, but many of you might not know, like, what exactly is cryogenic fuel and You might have heard stories of ISRO, like how it was declined, like how it made its Vikas engine and all, like its biggest cryogenic engine and all. So the thing is that these fuels are used in machinery that operates in space. Okay, and as it's written here that these are the fuels that require extremely low temperatures to keep them in liquid state. Now, why we are taking these particular fuels? Because obviously the environment in space is like at very low temperature, right? So since it is at very low temperature, obviously if we are taking some special type of fuel that remains in the liquid state, that will be like highly functional, and like that would be better, right? So these are the fuels that are used in machinery that operates in space, like where ordinary fuel cannot be used, obviously. Like we cannot take like ordinary fuels that we use, that is like in the liquid form in our room temperature, like let's say like petroleum or other products, other petroleum byproducts. But here what we use like cryogenic fuel, and due to the very low temperatures often encountered in space, as I mentioned earlier, and the absence of environment that supports combustion. So obviously, for like producing like combustion, we need oxygen, right? So that is also not abundant like in space, obviously, but in Earth it's easy. Now, one more point to add here is that the cryogenic fuels that are used most often, like it constitutes of generally the liquefied gases, and might know already, like these liquefied gases are like liquid hydrogen or like methane, liquid methane and such stuff. Okay, so I told about the cryogenic fuel. The third point is the GTO, which is the geosynchronous transfer orbit. Now, this is the full form, and I'll be coming to that in the just the coming slide. And then the apogee and the perigee. Now, this you already know. So what I'm saying, just think like we know, like let's say this is a kind of ellipse. Okay. Now we know by Kepler's law that the sun is present at any one of the two focuses on this ellipse, right? And any of the planet, let's say this is Earth or any other planet which is revolving around the sun in its orbit. So we know that this is the nearest point, let's say, to this focus, and this is the farthest point, right? Like it's not to scale, obviously. I'm making it right now. So this particular point is known as the aphelion. This particular point is known as the perihelion. This we know. You might have studied in your first semester some courses, might be. And the second thing is like corresponding to those particular aphelion and perihelion term, I'm introducing like not I'm like these two terms are there, like apogee and perigee. What are these? Just imagine that instead of sun, we are talking about the Earth. So let's say this is our Earth. This is the elliptical orbit around the Earth. The nearest point to the Earth from here is the perigee, and the farthest point is the apogee. That's it. Now, what is orbiter? Orbiter is another type of probe itself, and which travels through space, and it revolves around a particular celestial body. Then, what is lander? As the name suggests, it has the capability of landing on a particular celestial body and taking off back from it. Rover, as the name suggests, it like moves around the celestial body and any astronomical object, and like collects information about it. It uses solar energy for its function. The last one point here is that IDSN, which is Indian Deep Space Network, and it is an institution of ISRO itself, and it is located near like Bayala, Bangalore, Karnataka. Now, let's talk about the geosynchronous transfer orbit. So, the thing here is that what happens is that let's say this is our Earth, and different space agencies use different methods to um, send their spacecraft to this geostationary orbit. Now you would ask like, what is this geostationary orbit? I didn't mention it earlier. Yeah. So the geostationary orbit, why spacecrafts need to be sent there? So the thing is like, the geostationary orbit is a circular orbit, and this geostationary orbit is around 35,785 kilometers from the Earth. Like I'm talking about the its apogee wala part. Okay, the farthest point is 35,785 kilometers. And this particular geostationary orbit, all the spacecrafts are sent here. Now, why? Because communication satellites are often placed in geostationary orbit, because this particular orbit is at like that much distance from the Earth, such that with respect to the Earth, the rotation of that particular spacecraft will be constant. It means that when a person, let's say I'm standing here, so if I'm standing here and I'm seeing this spacecraft here, so this Earth would be like rotating from west to east. Let's say like this, it is rotating like this or like this. Then this particular spacecraft would be moving with the same velocity as the rotation velocity, angular velocity of the Earth. So it means that when I will reach at this point, like let's say this is at the, I'm seeing my spacecraft here. When I'll reach this point of the Earth because of rotation, obviously, like I'm not lying here. So at that point, this spacecraft would be at this point. So with respect to me, the observation, the person who is doing the observation from Earth, that spacecraft would be constant. Now, again, you would ask, like, why? What's the need of this? The simple answer is that so that the antennas that are receiving the information from these particular spacecrafts are we so that we do not need to rotate the antennas again and again, right? You might have seen in pictures and all, maybe in some documentaries, some movies, that you might have seen those radio astronomers, sorry, radio telescopes and all, which continuously like rotates, or like various antennas that keeps rotating, facing towards the sky. But in this case, they don't have to do that because they can, without even rotating, since the velocity and angular velocity are coinciding, they do not need to rotate and they can directly get the information. Okay, so the accuracy increases. Now, this thing, geostationary transfer orbit. So what happens is that when one particular spacecraft is launched from any space station, be it NASA or ISRO or anything, what happens is that first it is sent to this transfer orbit. Okay, let's say it's sent here from any point, it depends. Now, when once it's sent here, it starts rotating. Okay, what was that? Is someone asking something? Hello, am I audible?
Yes, you are audible.
Yeah, okay, cool. So uh, this transfer orbit is such that first the spacecraft is sent to this particular point. Now, what happens is that this is like very far away from Earth. So if we are sending, okay, so we need to send our spacecraft to this particular orbit. So first it is sent to this transfer orbit. Then when it reaches its apogee wala part, it gets like we use our thrusters and all to give it a burn. So this is the our orbit increases. This is orbit after burn one, then orbit after burn two, and then after several burns, it depends on the mission, it reaches the geostationary orbit. Now, can anyone answer me that why we are not sending our spacecraft directly to this geostationary orbit? It's very obvious, so you might try. Like, why
It
are we?
requires more fuel.
Yeah, exactly. So what happens is that there are 2 points. The first point is that our Earth is like if we are sending this to directly to the geostationary orbit, it requires much more fuel. And here we only once we reach here, like once we reach this orbit, we just need to give one burn here. So it like then again another burn, then another burn, like that. So it will reach our geostationary orbit. So that's most obvious reason that it requires lesser fuel, lesser fuel. Okay. Then just a second. Yeah. So another point to add here is that um, one second. Yeah. So here you can see that something like this parking orbit. So can anyone guess like what? Now I'll give one hint. Like this parking orbit is just 173 kilometers above the Earth's surface, and this is even smaller than the like the transfer orbit. As you can see, this is the transfer orbit. This thing is the transfer orbit. Like this is the transfer orbit, and this is the parking orbit, this smaller one. So can anyone guess like why spacecraft is sent to this particular parking orbit first? Anyone? Okay, so the answer is that first, like it's not particularly necessary that they would say they will some like they will be sending it to the parking orbit all the time, but mostly they send. Why? Because they send it to the parking orbit to check whether all the thrusters and all the stages are working properly or not. After that, they give it a boost. Like let's say this is the parking orbit, then it got a boost at this particular point, and then it reached this particular orbit. Like this is a transfer orbit. Again, it got boost and all. This is the equatorial plane. Okay. Now again, you are seeing another point here, which is like super synchronous transfer orbit. Okay. So this is like 65,000 kilometers, like even double than our geostationary orbit, right? Which was around 35,000 something kilometers. So why is it used? So now I'll be introducing you to another method of like sending satellites to the uh, space, like so that it orbits the Earth. And this particular method is also popular. Like apart from the method that I explained right now, a few months, this is another method. So what happens is that this is the super synchronous transfer orbit SSTO, and this is like geostationary orbit. So we are supposed to send our spacecraft to this geostationary orbit. So let's say this is the point. Okay, you might get confused. You might like don't get confused seeing this. It's like on the other side of the Earth. Okay, so let's say our spacecraft is moving like this, and it started rotating, and it has been sent to this super stationary transfer orbit first. Now you can see that this stationary transfer orbit is like the focus is like towards the end of this only. So sending it to its perigee is easier. Now once we send it here, it starts revolving around the Earth like this. Now just think with me. We are supposed to transfer our satellite or like a spacecraft from this particular superstationary transfer orbit to this geostationary orbit. So what we will do, just think, like let's say this is one ellipse, okay, and this is a smaller ellipse, okay. So you can see that this particular point, if we want to send from this larger major length of major axis in this of this ellipse is more. Major axis means like this particular length. So this length is much greater, almost double for this than this, as you can see. And so sending it to here is like a bit of problem. So the more larger you will make this diameter, sorry, the more larger you will make the length of the major axis, the more straight this particular line will become. So let's say this is like this, and I'm taking even more like sharper like this. So it will become a bit more straighter. Even if I'm taking like this, it will become even more straight. So I'm talking about that. So the more the larger major axis length is, the more easier it becomes in lesser fuel expense that we can send it to the geostationary orbit. So that's basically point. And which space agency uses that? So our very own, we know that, like not our own, like we know this name, like SpaceX uses this technology. Okay. Now I've given you all the prerequisites and all the kind of like methods and all how the spacecraft is sent to the Earth's orbit. How it's sent to the Moon's orbit, we will come to that also. Don't worry. So let's talk about the mission first. It has like the our Chandrayaan 2 mission had like four components. The first component is the rocket that will take this particular Chandrayaan 2, like the whole machinery to the Earth's orbit, and after that, the orbiter is there, the lander is there. Name was Vikram. Rover is there. Chandrayaan. I will go through each of them one by one. Okay. So the first of them picture is here, the GSLV Mark III. So first point and the foremost important point is that it was the most, it's the most powerful launcher to date that ISRO has ever used. Now it was another main point is that it was fully formed in India, like it was fully fabricated within the country itself. Then it was capable of launching 4-ton class of satellites. Here, ton like means 4,000 kgs around, I would say. Then GTO means Geo Transfer Orbit, as I mentioned earlier, and its components are the S200 solid rocket boosters. These are the rocket boosters. L110 liquid state, this would be the second stage, and third one C25 upper stage, which is the cryogenic fuel stage. Okay. Its lift-off mass was 640 tons and height was around 43.43 meters. Like it's huge, but lesser than the one that NASA and other space agencies use, but still like it's pretty huge. And then the exact model was GSLV Mark III M1, okay, which was used in the Chandrayaan 2 mission. There were two more models of this, namely GSLV Mark III D1 and GSLV Mark III D2. And these particular rockets were used in like the missions of like GSAT 19, which was launched in 2017, and GSAT 29 launched in 2018. And after that, after that, this GSLV Mark III M1 was used in 2019 in this Chandrayaan 2 mission. Okay. So let's dive deeper into this. It's booster, like these boosters, it's their height was like around 25 meters. Then two S200 solid rocket boosters to provide huge amount of thrust, obviously, for the lift off to reach the escape velocity and all. Then S200 was developed at Vikram Sarabhai Space Center. Then second one was the L110 liquid stage. There were two Vikas engines. This is the name of the engine, and designed and developed at the Liquid Propulsion System Center. These are the institution name where it was manufactured. Then The next point is that the third stage was the cryogenic fuel stage, the C-25, India's largest cryogenic engine designed and developed by the Liquid Propulsion System Center. These are just the names and all. And cable 4-ton class, I've already mentioned here, that it can send 4-ton class satellites to the geosynchronous transfer orbit. Some more additional fact was that this was the most powerful launch vehicle used, and three stage, as I mentioned, two solid straps and a core liquid booster for to give it a boost like more thrust, and then third one was the cryogenic upper stage. The powerful cryogenic stage of GSLV Mark III enables it to place heavy payloads into low Earth orbits of 600 kilometers of altitude. It means like if you want to send a particular a payload of around 600 kilometers to the a payload to 600 kilometers altitude, that is designated as a lower Earth orbit. Like geostationary orbit is like much far, like around 35,788 kilometers is 600, which is like nothing in front of them. So this is known as a lower Earth orbit. You can check it out, like what are all the designations, like which are the parts like lower Earth, then lower Earth orbits, and what are more types of the orbits. You can easily find them. So payload, what is payload? So payload means like the what are the stuff that you are sending. It can be any satellite, it can be any like maybe like I would use the term maybe Vyomonaut, because the recent mission, that Gaganyaan mission, you might have heard about it. ISRO is about to do that, and the astronauts that would be sent to the moon by India, they they will be known as the Vyomonauts. Anyways, so payloads is the whatever the steps you are sending to the moon, sending to the space. Okay, then let's come to the orbiter, the second point. So this orbiter, it was installed around 100 kilometers above the moon, okay, not Earth. Note this point, and it consists of 8 instruments. Okay, so I'll not be mentioning all of them, but I'll try to mention the important ones. Then its weight was around 2379 kgs, and electrical power generation capability was around 1000 watts. Obviously, with the help of, you can see this solar panels and all, with the help of like solar energy. Then precise launch and mission management. Okay, so ISRO earlier thought that they are sending it for around like it will be function for 1 year only, but later on they confirmed like it was capable of having a mission life of around 7 years. Okay, so it is again a big achievement. And this I gave one question in my abstract of the talk, if you have read it, that was really Chandrayaan 2 a failed mission? So this orbiter will give us the answer, because this is still functional. Okay, so it was supposed to make communication with the IDS and the Indian Deep Space Network. I've already mentioned it. Then the Vikram Lander. We'll come to that. What is Vikram Lander? Dimensions are mentioned, propellant mass and operating on solar power I have mentioned. And it was supposed to make loop of information passes. Like there would be rover. That rover would send the information to the lander. Lander would send to the orbiter. Orbiter would send to the ISRO. Like IDS, and I would say, okay, I'll come to that. It's a kind of chain of communication. There are some more additional facts. It had 8 instruments. So these are some important ones. Like it had the imaging infrared spectrometer. And what is this? I'm not going into details, but what it was, why it was situated in that, because to identify the minerals and to indicate the presence of hydroxyl and water molecules. When see this, so it means that it obviously had, like I've already mentioned earlier, that it had the remote sensing technology. And the thing is that this you can find out whether the hydroxyl atoms, ions, or like these water molecules are present on the moon surface from 100 kilometers above the moon. Like it's pretty mind blowing, right? So that's what the use of this infrared spectrometer. Then obviously it's still functional till date. Okay, now let's come to the Vikram lander. And unfortunately, this Vikram lander where this problem started. So it was, as the name suggests, Vikram. So Vikram is like Dr. Vikram Sarabhai, the father of Indian space program. You all might have heard about him. There's some one popular show on, like I don't know, like Sony Live or something, known as Rocket Boys. So they're also, it's pretty good. Which have shown like about ISRO and like its early stages, like how it developed and all. You can take a look at that. So its weight was around 1471 kgs. Dimensions are mentioned here. Then electrical power generation capability of orbiter was 1000 watts, and in this case it is 650 watts only. Payload 4 means like 4 instruments or 4 steps you can send to the sent with it. Touchdown velocity. Now, can anyone tell what is touchdown velocity? Anybody? Anyone? I'm audible, right?
Maybe at which velocity it touches the surface of moon.
Yeah, exactly. So the touchdown velocity means the velocity at which it would touch the moon, or I would say it would the velocity just before it touches the moon. Okay. Now its landing site was the high plain between two craters. Don't go into names and all. These are the coordinates also I mentioned. And they also predicted that they also thought like in case something adverse happens, then they had an alternative site which was with this like 67.7 degrees south and 0.4 degrees west. So what it means, like let's say this is the lunar surface and these are the, let's say these are the craters. Okay, so this is some a large area. So this lander was supposed to be like uh, this lander was supposed to be landed here. Okay, then lifetime is one lunar day. Can anyone tell what is one lunar day? Lunar day. Yeah, anybody? Any guesses? Like in Earth days, one lunar day is like
Length of day in moon on moon.
yeah, that's correct. But like, how many days in Earth's perspective? Like, if you are spending one day on,
27 days.
no. It's like I'll mention that it's like 15 days on Earth. Okay. You might have seen the Interstellar movie. There, they say I don't exactly remember. As I saw it like a long time back, where it says like 1 minute here, or like 1 hour here is around 7 years on Earth, something like that. So, like I'm just giving one random example. So it's like one lunar day means like 15 days on Earth, approximately between 14 and 15 days. Okay. Propellant mass. What is propellant? Propellant means the fuel. It was around 845 kgs. Total weight was 1471 kgs, and the propellant mass was around 845 kgs. So the total mass of the lander, if you remove the propellant mass, was this much. Okay. Then 1471 minus 845, whatever it is, around 600 kgs. Now it was supposed to have constant communication with both IDSN as well as the orbiter as well as the rover. And one more point to add here is that the rover was situated inside of this lander. Okay, like their plan was like the lander would reach the lunar surface. After that, lander will deploy, no, release the that release the rover on the surface. Okay. One more thing that you might have seen, like one only 15 days, right? You might be thinking like only 15 days is pretty less. So yeah, it is pretty less. And as compared to its counterpart orbiter, which is still functional and has been speculated that it would be functional for around 7 years, means around from 2020 to 7 years, I would say around like maybe 2025 or 2026. So 15 days only, right? And it was supposed to carry out all its stuff in those 15 days itself. Some additional fact is that Pragyan rover was only 27 kgs inside. I will come to that. It had 5 legs with 3 instruments on board. Now, what were those 3 instruments? And I already mentioned that its payload was 4, and 3 instruments were loaded on this. They are the radio anatomy of moon-bound hypersensitive ionosphere. Don't go into names; these are pretty complicated names. Atmosphere probe Rambha. Its name was Rambha. And why? What was the use of it? It was made to measure the density of the lunar subsurface, like the not the surface but the subsurface, and the changes that are occurring throughout that time, or changes around it. Second one was like this Chandra surface thermophysical experiment that was supposed to be used to measure the thermal temperature around the south pole of the moon. So again, I told in the beginning, like it was supposed to, it was a pretty complex mission. Like they aimed a lot of things. Like they would find out about the moonquakes, about the temperatures, about the density, about the early evolution of solar system, like lot of stuff. So this was supposed to measure the thermal temperature in the south pole of the moon. And the third one was the instrument of lunar seismic activity, ILSA is its short form, to measure the moonquakes. Now, what are moonquakes? You might have heard about the earthquakes. It is the counterpart of the counterpart of the earthquake itself, the quakes on the moon, or you can also call them as tremor potential of the region. It is a scientific term. Now, its initial design was made by ISRO, the Space Application Center, Ahmedabad, and later it was developed by the URSC Bangalore. Okay, so you can see this picture is like, I really like this picture because this is the actual picture of the Vikram Lander, and you can easily see like there are like one, two, three. I can see three, maybe like two legs. Behind it was five legs. You can see how huge it is as compared to the like, scientists. Okay, anyways, let's go to the Pragyan rover. So this Pragyan rover was a six-wheeled robotic vehicle. And what is the meaning of Pragyan? Pragyan means wisdom in Sanskrit. Okay. It weighed only 27 kgs. It was very small. As you can see, the dimension it wasn't even like exceeded 1 meter. Okay, in like length, breadth and height. Then its payload was only two. So the solar energy was supposed to be used for power generation. You can easily see in this particular figure that this is the solar panel. And communication, it was supposed to make only with the Vikram lander, and its speed would be 1 centimeter per second, which is pretty less. It was slow, but yeah, it was again like supposed to cover around 500 meters on the surface of the moon. So only 500 meters you must be thinking, right? So in that particular 500-meter only they were supposed to carry out all those, like the rover would move on in those would have moved on the surface of the moon on that 500 meters and would have carried out its experiments and all. Its life was same as that of the lander, which is one lunar day, which I already mentioned, like around 14 to 15 days. Now, I mentioned earlier this that it was made and like a chain of communication would be formed where this rover would send to its information to lander to the orbiter to the ISRO center or the IDSS. Now, this whole chain of information was supposed to take around 15 minutes. Okay, and it had two instruments on board. I mentioned one of them, and the first one was the laser induced breakdown spectroscope (LIBS), whose main objective was to identify the elements present near the landing site. Now, how it will identify the elements near the landing site? So it had this laser, it would fire this laser pulse, and that laser pulse would cause the like this laser pulse would be fired at different locations in that particular 500 meters itself, and the radiation emitted from those particular regions where that pulse is getting fired, it would check the decayed plasma, and it would analyze that, and then it would, with the help of spectroscopy techniques and all, it would like predict which type of element is present there. Okay, yeah. So now I've already talked about like how like I'll mention like I've already talked about what was the aim of this particular mission. Then I mentioned like how the launch happens. I gave it extra details also. Next, I talked about the different components of this particular mission, like the rocket as well as the orbiter, the lander, and the rover. Right now, we will go to the mission details. So now we will try to like constitute all of these. The first one was the launch. It was 22nd July 2019. Launch site Satish Dhawan Space Center, Sriharikota. It's in Andhra Pradesh, I guess. Lander orbiter pair went into initial elliptical orbit. Now see, the lander orbiter pair. You already know, like it's pretty obvious that the rocket that is going, it will carry this orbiter, this lander, and this rover together, right? Now at some point it will have to like at some point this orbiter will stay in the lunar orbit, and whenever I'm using the word lunar, it means the moon. Okay, so whenever like that particular orbit like in that particular lunar orbit, that particular orbiter would be revolving, and at some point this this lander would detach itself from that particular orbiter. Then that lander would use its own fuel. I've mentioned like around 845 kgs. I mentioned here, I'll show once again. So it had the fuel of around this propellant of 845 kgs. It will use this propellant to to land on the lunar surface, right? And that particular lunar surface, and after where once it reaches that lunar surface, it will give its way to the rover, it will deploy the rover on the surface, and then rover would carry out its mission. Pretty cool, right? Now, this particular phenomenon, like I mentioned, like how it reaches the Earth orbit, right? And I mentioned then, like I will be explaining how we reach the lunar orbit from the Earth orbit. So I'm going to that. One that particular method is known as the translunar injection. Okay, or the land orbit separate. And once the lunar orbit insertion happens, it means once it reaches the lunar orbit, then it detaches the land. Then lander detaches itself from the orbiter. Now the orbiter would be revolving from the 100 kilometers above the circular orbit of the Earth. Okay. Now see, this particular picture I've taken from the web itself. Now you can see one thing here. I'll be asking few questions. You all can try to answer. I've already mentioned that let's say this is the geostationary orbit. Let's say, and we want to send this to the moon. Okay. Now I'll be mentioning two. Let's say this is revolving like this, like Earth is revolving in this direction. Okay, Earth is revolving in this direction. This now since Earth is revolving in this direction, the direction in which it is revolving, that particular hemisphere I'll be called. That particular hemisphere is the one hemisphere, and the other hemisphere would be the opposite, where the opposite side of the rotation. So that particular these two hemispheres have been named. That is the leading hemisphere and the trailing hemisphere. Okay, so what happens is that let's say in this geostationary orbit, this particular satellite or this particular rocket is revolving. Now you can see an 8 is getting formed, right? Like just see, I'll make the 8 here. Let's say from here to it went here, then it went here, let's say like this, right? A kind of 8 you can say. It's now the most obvious question that should come in your mind is like why we are not sending this particular orbit via this side. And I'll be mention one thing, like let's say this moon is also rotating on this side itself. So can anyone guess why we are not sending our orbiter and all from this side, and why we are choosing this 8 wala round path? Can anyone guess? Like let's say this is the Earth, this is the moon. So why we are sending it like this? Why we are not sending it directly to this? Can anyone guess? Think. I'll give one hint about like angular momentum conservation. Anybody?
It depends on the velocity.
Hmm. Okay, like no, but like I'm defined like generally, it like even if you talk about the Apollo mission, that also used this particular method only. It was like pretty long time back. It's still it's been used. Why? Like there must be something with it. Okay, so I'll mention that. So what happens is that if the velocity is towards this, so if we are going using this path, like let's say it's like this, okay, like this, if we are sending like this, then what happens is that once it comes under the influence of the moon's gravitational force, since its velocity is more, it will try to fly around its tangential velocity. So it will it might accidentally go to a higher orbit, like a bigger ellipse than we need. Okay, and if we are sending it on the opposite side of the rotation of this moon, I've already mentioned this is the side of the rotation. Moon is rotating like this. Okay, like on this side it's rotating. So we are sending it from the opposite side. So there is a chance that we keep the thing as like a bit of what the orbit a bit less. So yeah, so that's the reason. So once it is going through this particular path, if we are taking, let's say from this path, it might right now when it reaches this path, this is the trajectory, initial trajectory. Okay. So one point I want to mention, from Earth, what we were doing, from Earth, we started from inner side and went to outer side. From Moon, we will start from the outer side and go towards the inner side. But what is happening? If we are using this particular, like the side, the leading hemisphere of the moon itself, as our side from where we are sending our probe, then what happens is that because of this angular momentum, extra angular momentum, its velocity might increase. Sorry, its velocity, when it comes under the force of this moon's gravitational force, it might goes towards, like it might it might go into even bigger orbit. So that will be a problem for us. It will require more fuel and all. That's why this opposite route is chosen. So first it will reach this, and again the same thing is that instead of giving it a burn at this particular point, we will try to reduce its velocity. Like first it will be in the, let's say this is the moon, and our orbit, like this is apogee, this is perigee, whatever. Then at this particular point we will try to slow it down a bit. Then again we will slow it down a bit more. Again we will slow down a bit more unless we reach the place where we want to meet. Now here only the problem happened. What exactly went wrong? So what happened was, like, on September 7th, 2019, this Vikram lander was supposed to be at 55 degrees tilt. But what happened was, like, due to some technical lag or whatever might have happened, like any particular concrete statement wasn't there, like I couldn't find. It was at around 410 degrees instead of 55 degrees. Okay. And since this Vikram lander was an autonomous mode, scientists at the ISRO were not controlling it, so they didn't know what exactly was happening with it. And because when it was at 400-meter away from the landing site, they lost the connection. And its velocity, because of this extra tilt, its velocity was higher than the touchdown velocity was around 2 meters per second. It was higher than predicted, so it suffered a hard landing. And because of that hard landing, all the things happened. So this is the official statement from ISRO chief, then ISRO chief K. Sivan. The lander's velocity was supposed to be reduced from 6,000 kilometers per hour to 0 kilometers per hour in just 4 phases. But in the span of 15 minutes, what happened in this? There was some problem in the second phase. Because of that second phase, the things went adverse, and third phase couldn't handle it. So yeah, the fun fact with this was that while Chandrayaan 2 was developed at a cost of 978 crores, this Chandrayaan 3 mission is being developed. It's about to get launched, and its estimation is just 250 crores. Okay, it's like magic. I don't know how they do this. It's like very, very cost effective. And for Chandrayaan 3, the orbiter from Chandrayaan 2 mission would be functional. So I told, like, orbiter is still functional. It will be functional for 7 years, around till 2025 or 2026. So we can use the same orbiter. So they don't need to pay for that separately now. Only mandating a lander and a rover for organizing second attempt. So with the help of this Chandrayaan 3 mission, I hope that they will be able to achieve this soft landing. So the final point I want to mention here is that was this really a failed mission? So in my opinion, it wasn't, because the main part of this mission was the orbiter, right? Now this particular orbiter is still functional, and since it is still functional, it is still sending the information to from the lunar surface to the Earth, and it will be used for the future Chandrayaan 3 mission as well. And if you will see that 7 years in front of those 15 days, I know that 15 days they were supposed to do a lot of stuff, that particular rover and the lander, but still, those 15 days, it was a failure, I would say. But the major chunk was this orbiter, and it was mentioned in a statement also that it is pretty much successful mission, not fully successful, I would say. So yeah, they learned a lot of things with this, and maybe I hope that with Chandrayaan 3 mission they will try to uh, do the soft landing. So yeah, here are the few sources that I've used for this. So that's it. I'm open to questions if you want to ask one. What just happened? Am I audible? Hello. What is happening? Yeah. Uh,
Yeah, guys, if you have any questions, you can ask now.
so are there any kind of questions, any clarifications, anything you want me to like explain again? So I'm open to questions. You can ask me. I hope you learned something about it.
Excuse me, sir.
Yeah, yeah.
Sir, can you repeat that part when?
Don't worry, sir. Yeah, yeah.
Uh, okay, Arjit, can you repeat that
Sir.
part when the satellite was moving from SST to that geostationary orbit?
Okay, okay, yeah. The one that they were using for that that's used for by SpaceX, right? The second method. Wait, 1 second. Is my screen visible?
Yes,
Yeah, this one, right?
yes, yes.
Yeah. So what they do here is that they send this particular satellite or this particular rocket to this bigger orbit. Like it's the length from Earth, like this distance, the apogee is around 68,017 kilometers. Okay. And this is
It's
the
like
geostation.
can it go directly to the geostationary orbit? Like what is
No,
why?
no. Why now you yeah, I got your doubt. You might be thinking like why we are sending it to the bigger orbit, right? So what exactly is
Yeah, yeah,
happening?
yeah, exactly.
Yeah, yeah. What exactly is happening here? You can see that this Earth is at around, approximately at the center of this geostationary orbit, like this distance, and this distance is approximately same. So if you want to send this space craft to this geostationary orbit, you will have to send it to these 2 points, or maybe to these any of the points on this ellipse. But here you can see, if this is Earth, then this is superstationary transfer orbit is like this. Now you can easily send it here, right? So this will require much lesser fuel. And since your geostationary orbit is intersecting to this geostationary with supersynchronous transfer orbit, you can give it just one burn and then you can reach this next orbit, like geostationary orbit. That's the main point. Is it
Okay.
clear now?
Yeah, yeah, thank you.
Yeah, okay, clear. Any other questions or clarifications?
Is the orbiter sending
Yeah,
any
did you still
information?
question?
Uh, yeah, yeah, yes, Sri Sai. Hello.
Uh,
Yeah.
yeah, what it is related to?
Related to means
What information does the orbiter send?
what information the orbiter.
Sends
No,
to
his
Earth.
question was like,
The orb.
like,
Someone,
like that at
someone, are you
they
saying
asked
something?
like what information was it?
Okay, okay. The thing is like this particular. Wait, are you asking about the orbiter of the Chandrayaan 2?
Yes,
Yeah. So this particular Chandrayaan 2, as I mentioned, that it is still like scanning the lunar surface of the moon, and it's still like sending the information. So are you asking me like what particular information it has sent till now?
yes, yes.
The main thing was like I don't exactly remember, but like it discovered some new elements on moon. So and some uh, I can't exactly recall like what found.
I can help
Mm,
you with that. Like like last week, I guess. So it
huh?
had like discovered argon gas on the moon's exosphere. Is it audible? Am I
Yeah, yeah,
audible?
your voice
Hello.
broke in between. Yeah, now it's audible.
Uh, yeah, like last week there was a news that like the Chandrayaan 2 mission had like discovered argon gas in the exosphere of moon. So yeah,
Yeah,
that
yeah,
was
exactly.
the recent discovery.
Recent discovery.
So
Like
yeah,
it was
similarly you can
dated.
like there are like some few other discoveries as well. You can check it out.
Yeah.
And one more question.
Hmm.
Why do we want to check for water on moon having many water resources on Earth?
Okay, this is a kind of okay. This question is like see the thing is like we I would say the curiosity, like whether like whether water really exists on moon or not. Obviously, the water that even exists on moon, it's not in liquid state; it would be in some other state. So the it's kind of philosophical question. I would say like it's kind of question like you're asking that why are we trying to live colonize Mars if we are living on Earth itself. So it's like the primary answer is that the um, primary answer is the curiosity itself. Like we want to know more about our own satellite. So yeah.
Okay.
So any other questions or clarifications, anyone? Okay, if not, then perhaps yeah. Thank you, like Celestic, for this chance, and yeah, I guess we can end.
Okay, Arjit, that was a great talk, and it was super informative as well. Explained all these concepts super
Your
nicely.
voice is breaking
I'm
out.
sure everyone understood whatever was spoken. And yeah, thanks
Yeah.
for being here and giving this talk. And if anybody has any additional questions, they can either mail Celestic or if you're in the WhatsApp group, ask it there itself. So if we can end the session.
Yeah. Okay. Yeah, thanks a lot. Thank you everyone for joining.